Welcome to Covalent Chemistry. In this screencast, I'm going to talk about molecular structures involved in covalent bonding. I would tell another chemistry joke, but all of them are gone. A structural formula uses symbols and lines to represent the arrangement of atoms and bonds within a molecule. It gives you somewhat of the idea of the three-dimensional arrangement. Notice that here in CH4, it looks as if these bond angles are 90 degrees. They're not exactly 90 degrees, but this still gives us somewhat of the idea of the arrangement of the atoms in that molecule. When drawing structural formulas, one should follow these steps. The first thing you're going to want to do is to add the number of valence electrons contributed by each atom in the molecule. Then you need to decide which atom is the central atom. In general, the central atom has the greatest need for electrons, is listed first in the formula name, is the element closer to the left on the periodic table, and it can never be hydrogen. And my question for you today is, why can it never be hydrogen? All right, well, who remembers that hydrogen can only form single bonds? If hydrogen can only form single bonds, then there's no way that it could be the central atom because you could only attach one thing to it. So remember that hydrogen is always going to be on the outside. That's referred to as a terminal bond. The next thing to consider in drawing the structure that allows is that you must draw a structure that allows each atom to obey the octet rule, with the exception of hydrogen, which of course is going to obey that noble gas rule of 2 electrons. Then you need to add electrons for each negative charge and subtract electrons for each positive charge. Finally, you should check to make sure that the total number of electrons that you calculated in the first step is the same as the number of electrons that you've drawn. On to an example. Well, if we have methane, which is CH4, we need to calculate the total number of valence electrons. Carbon has 4, and hydrogen has 1 each. So we would take 4 times 1. That would give us a total of 8 valence electrons. So we know that we have 8 total. Next we have to decide what's the central atom. Well, carbon is listed first, so that should probably be the central atom. Also remember, hydrogens can only be terminal atoms, which means that they have to be on the ends of the molecule. And so then we can draw something like this. This arrangement is referred to as the skeletal formula. It does not show the dots for the electrons, but it does show where the atoms are located. All right, so now I want to fill in my electrons. So I have 8 total electrons, and so I can draw in 8 dots. And what then is the type of bonding that we see here? Yes, you guessed it. These are all single bonds. Now the other thing, remember, that I can do is I can show a structural formula as a line or a dash for each pair of shared electrons. So in the case of methane, I can draw it just like this. It's the same as with the dots. All right, the next example, propane. Well, now we have C3H8. So 3 times 4 plus 8 times 1. So that would be 12 plus 8 is 20 electrons altogether. And then I want to draw my carbons all in the center of the molecule because we know that hydrogens can only be on the outside. So then I can just start drawing hydrogens. Now remember, the other thing to keep in mind is that you do want this to be as symmetrical as you can possibly make it. So let's put 3 hydrogens on each of the outer carbons. And then on the center carbon, notice that it's already forming bonds with the other 2 carbons, so there's really only a spot for 2 hydrogens. So does that give me 8 hydrogens? I believe it does. So now what I can do is I can start drawing in electrons, and I can count as I go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And notice that I end up with all single bonds once again. Notice also that these 2 compounds end with the same suffix, ane, which is ane, and that refers to the fact that these are classified as alkanes. there's a little bit of organic chemistry for you as a bonus for today's episode. Now for some more practice, so stop the video, draw the structures, and then tune back in to see if you did it correctly. Okay, off we go. The number of valence electrons, 2 times 4 plus 5 plus 6 plus 1 is the total of, well, let's see, 8 and 5 is 13, 14, 20. So the structure should have 2 carbons bonded together, and then 5 hydrogens, and then an oxygen, and then a hydrogen. Notice that the structural formula is somewhat given to you by the molecular formula there with the C2H5 indicating that these are all hydrogen bonds connected to those carbons, and then we have an oxygen and a hydrogen on the end. Alright, and then acetic acid. Well, I'll leave you to figure out the valence electrons, but the structure, again, if you look at the hint given to you by this molecular formula, is that it's CH3C, and then there's 2 O's attached to that carbon, and then an oxygen, or rather, 2 O's and then a hydrogen on the end, and then you've got 2 pairs of electrons, lone pairs, on each of those oxygens. Over here we want to finish out the structure with the other hydrogens. There we go. So resonance occurs when more than one valid Lewis structure can be drawn for a molecule or ion. So you can see here that this is oxygen number 1, and this is maybe oxygen number 2, and this one is oxygen 3 in each of these diagrams. So 1, 2, and 3. And then you'll see that the double bond moves around from this position to this position to this position. So each of those are different oxygens, and so that means that these are 3 valid Lewis structures for the nitrate ion. So resonance structures differ only in the position of the electron pairs, never the positions of the atoms. If you noticed in that last structure, the N was in the center for all 3 of the resonance structures, and the oxygen atoms did not move. The double bond is what moved. It's important to note that each actual molecule or ion that undergoes resonance behaves as if it has only one structure. The actual bond length would be an average of all the bonds. So in that last structure we had 1 double bond and 2 singles, so the average would be whatever that works out to. But all 3 of them would really possibly exist at any given moment in time. Alright, exceptions to the octet rule, because we always have exceptions. The first one is NO2, and if you add the electrons there, you have 5 plus 2 times 6 is 12, so that's 17 electrons. That should already look odd to you. So when you draw this structure, you'll end up with N, double bond O, single bond O, and then you have lone pairs on the oxygen and on this oxygen. So now we have 2, 4, 6, 8, 10, 12, 14, 16 electrons. The 17th electron belongs on that nitrogen. Notice that nitrogen started off with an odd number, it ends up with an odd number. This is obviously not very common, but it does happen. The second exception would be molecules that have less than 8 electrons around the central atom. And of course that would be our good old friend boron trihydride, which is going to be something like this. Or you can have anything really that has only 2 atoms. This hydrogen here is only going to have 2 electrons around it. The boron here has only 6. Each of the hydrogens only 2. So all of these are exceptions to the octet rule with less electrons than 8, with the exception of the chlorine over here, which does have 8. And finally, molecules that have more than 8 electrons around the central atom are called expanded octets because they have more than 8. So we would be talking about something like PCl5, which we've looked at previously. Looks a bit like this. Something along those lines with the extra electrons. Notice that the phosphorus ends up with 5 bonds or 10 electrons around it, and so that's definitely an expanded octet. Note also that elements in the third row or below are the only elements that can do expanded octets. You cannot have an expanded octet in a second row element. They're just too small for that.